Let's open up TutorTIMS Cloud and load Sallen-Key filter design, second order, and implement the transfer function using the Laplace Biquad. So it's a continuous time design using a single Laplace Biquad module. Click on plot and that opens up an interactive display of the poles and zeros that relate directly to the transfer function which is implemented by the coefficients. Let's average the FFT over a period of time, open up the time base so that we have a closer look at the frequency domain. You can see the red signal is the noise, the wideband noise going in to test the implemented filter, and the blue is the response. We'll turn off the incoming signal because that doesn't change, and we'll just be looking at the blue signal, which is the output in the time domain and frequency domain. As you can see, it's a low-pass filter, and now we will explore what happens when we change various coefficients and how they relate to the poles and zeros. So at the moment we have a design which has 2 poles and no zeros. If we change the A2 coefficient, that by changing the A2 coefficient we will be changing the omega-2, the natural frequency of this design. And as we change it, you can see it is now has a radius of approximately 2.7. And because the omega, the natural frequency omega has increased, the frequency of the cutoff point has also increased. It's moved to the right. Notice that the blue spectrum has moved to the right. And as well, it's not as flat in the pass band. It's now become a little bit more peaky as the poles move closer to the J omega axis. Now we will explore varying A1. Now, reducing the A1 coefficient increases the Q of a signal. And that's because A1 doesn't affect the omega of the denominator, but it affects the Q of that transfer function. So it basically moves the poles closer to the axis, and as you can see in the spectrum, it has become a lot more peaky, a much higher Q at the cutoff frequency. This is not usually very useful in a low-pass filter, but it serves as an interesting example of the relationship between the coefficients of the denominator of the transfer function and the poles and zeros and the real-time response. Now, as we move very close to the axis, the filter starts to oscillate. You can see that the response in the time domain is getting very large, and the closer you get to the axis, you'll actually send the filter into oscillation. We move the poles back away from the axis. Notice that the poles always stay on the circle. The circle has a radius of omega-0. Okay, we've changed the coefficients such that the poles are now away from the axis. Now we're having a look at the numerator, which sets the zeros. Let's just arbitrarily add a value to B0. And now we have B0 is set to 1 and B2 is set to 1. That has created 2 zeros, which you can now see on the J omega axis. And because those zeros are on the axis, it causes a very deep notch to occur in the filter at that frequency. So as the frequency of interest moves up the axis, you can see we travel into a notch, from DC into a notch, then up until a slightly peaky response, which relates to the poles. So poles are responsible for creating an amplification of the response, whereas zeros cause a nulling of the response. If we look at the S-plane, the vertical axis, the imaginary axis, relates to the frequency of the response of the transfer function. So we'll draw that in there with this green arrow in the vertical. The equivalent on our scope display of the frequency response of our scope display is the horizontal. We'll draw that in. So that's frequency, this is frequency. Let's mark 0 Hertz DC on the S-plane, and let's mark it on the scope. So as you consider the frequency moving from DC up towards the frequency at which the first 0 is, the transfer function's value will tend to 0. And hence the frequency response of the circuit, of the filter, tends to 0. As we move further up the frequency, approaching omega 0 where the pole is located, the pole will cause the transfer function to be amplified, to be greater than unity. And that's why we get a peak in the frequency response. And then as we move off to the high frequencies, it just flattens out to the long-term value. Because the zeros are the numerator of the transfer function. So when they go to 0, the entire transfer function goes to 0. However, the poles are on the denominator, and when they go to 0, the transfer function goes to infinity. And that's the interesting difference between zeros and poles and how they affect the transfer. By careful placement of poles and zeros, we can design or optimize a filter. And the purpose of this demonstration is to show you there is a relationship between the mathematics of the transfer function, the numerator and the denominator, as expressed in a pole zero diagram, and as it implements in the real world as an actual filter response. So there's a complete relationship between these three, shall we say, entities, these three properties, these three concepts. So now you can see B0 has been changed. The zeros have gone up very close to the poles. So the frequency of the 0, as we start from DC, the cursor goes down into the notch, into the trough due to the 0, then up due to the peaky response due to the pole.